Hi guys, thanks very much for having me. My name's Jim. I'm talking today about some work I've been doing with my mate Shosh over... That's it, you're go. I'm talking today about some work I've been doing with my mate Shosh over there, with some helpful input from Andy Gelman and Mike Betancourt on a beautiful technique called Aggregate Random Coefficients Logit, which is a little bit tricky to implement in Stan, or it was at least. I want you to picture yourself as the owner of a bodega in New York City. So we've got these little corner stores on every corner, and that's where you buy your beer. And you can walk into one of these stores and you get a fridge there, and it's got 45 different types of beer. And you will eventually make a choice, or maybe you won't. Maybe you'll just walk away. But the owner of the bodega has to choose prices for all of these beers, and they want to do so in such a way that they maximize their profits. So this is a problem we're working with. Now, how would an enlightened bodega owner maybe do this? Well, a naive approach might be to run some A/B tests, some randomized controlled trial where they experimentally vary the price of their beer. And if they were to do so, they might notice that when the price goes up, people will buy less of the stuff. When the price goes down, people will buy more of it. And so you could trace out a curve a little bit like this. If the price is 0, your revenues are going to be very low. No matter how many you sell, multiply it by 0. If you stick the price way, way, way up, you get the late night, people who are really desperate for beer, but you're not going to sell that many units, and so your revenues aren't going to be great. So somewhere in between there, you've got a sweet spot where the revenues are going to be maximized, okay? And you might think, well, I've done this experiment. I've traced out this partial revenue curve with respect to price. I've done experimental variation. There's no endogeneity problems in the price variation. So what happens when I stick that price where it ought to be, at this maximum? Well, let's decrease beer 1 price to about $2 or $1.90, somewhere around this summit. Well, what's happened? Look over here. We get an increase in sale, or we've got unit sales market share, we've got revenue market share, we've got revenues for this beer over here. Let's call this beer over here, it's a, Stella, okay? Now, so we've dropped the price of Stella, the sales have rocketed up, but what's happened over here? Well, we've got one of the competing products has now lost market share to Stella. So those people who are going to the fridge, they're walking in there, they see Stella's on sale, the price is really low, and they no longer buy their Heineken. So it's a close substitute. I think it's actually the same stuff in a different bottle, but it's cool. Now, what hasn't lost market share? Well, that's like your really nice, Bell's Two-Hearted Ale, a beer that is close to my heart. That hasn't lost much market share because it's not actually all that close a substitute to Stella. Okay? What has happened in Aggregate is that they have decreased their revenues over the entire portfolio of beers that they sell. And this is a problem. So that's the business problem. The technical problem, we've got several technical problems here that we're trying to address today, is we have situations in which we only have aggregate data. And this is a situation where you're a market research firm, or you're doing research for, say, a car company or a wine company, or a wholesale beer seller, and you can get market shares data or aggregate sales data, but you can't get the actual sales of your competitors at the unit level. I can't get the actual people who are purchasing that beer. And so we only see aggregate sales. Now, I really like Pilsners. My wife's more into ales. And you can imagine there'll be 2 different types of beer. Now, what happens when a new Pilsner comes on the market? That's going to affect my choices far more than it affects my wife's choices, okay? Now, if we were to aggregate across individuals, where each individual has their own choice function, where they take the information that's available to them in order to make a choice, If we were to aggregate across that, then this isn't necessarily going to be the same, any effect that we see, any price elasticity or market shares from a new product, is not necessarily going to be the same thing as if we would have some model that's trained only on aggregate data. So if we were to introduce a new Pilsner, that's going to change my purchase probability for the existing Pilsners much more than it will my wife's. Okay, another big problem is that we have endogeneity in price setting. Now, what does this mean? Okay, so we've got Bell's two-hearted ale over here. The information set has a whole bunch of observables, X. This will be like how alcoholic it is, what its hops rating is, what its price is, what colour label is, etc. And then we've got psi, which are the unobserved variables. Both of these variable types influence the price that is charged for the product. The bodega owner observes X, they observe psi. Okay, psi might be the coolness or the quality or something like that isn't really easily measurable, but is definitely there. It also influences my happiness. And so these two things are going to be correlated with price and happiness. And that makes it quite difficult to implement. Third problem is strategy in price setting. So you can perhaps imagine a world where you've got a frequentist and a Bayesian and they're arguing, and you observe their conversation when they're arguing. And then the frequentist leans over and punches the Bayesian. Okay? Now, how do you expect the Bayesian to respond? Well, you've never observed the Bayesian throwing a punch, have you? But you're not going to say the probability is 0, right? So exactly the same thing in marketing analytics. We want to make a prediction about what's going to happen when something unprecedented has happened in the X's, when we change some variable. Because we have prior knowledge about how people behave, about how firms behave and what they are optimizing. Okay? Similarly, when we're actually constructing the likelihood, we need that likelihood to be centered around the market equilibrium that we think that we should observe, given the structure of price setting. We'll get to that in a second. So, one model that does all these three things is the aggregate random coefficients logit model. Cool. So the aggregate coefficients logit model is a model of individual behaviour. But remember that the data that we observe is at the aggregate sales level. So the trick is that we really need to generate inference for what the individuals are doing, but we never observe any individuals. But we want to start with the generative model at the individual level. So what is that generative model? Well, it is that each person who walks up to that counter and sees all the beers, those beers they flash the person with some utility, okay? And the person is simply going to make the choice that maximizes their utility. They're going to purchase the beer that gives them the highest happiness. They might get flashed with all these beers, but then there's like the don't buy a beer utility as well. So they can always take this outside option of walking in there going, they've only got Beck's and walking straight out. Okay? Now, what is this utility? So we never observe utility. This is an important, very, very important point. This U, we never observe it, but what we do observe are sales. Now, so we have X, which is for product J in market T. X is the observed information. And each individual has their own parameter vector on X. So those beta i's are unique to each individual. So that sounds a bit crazy, remember, because we don't observe any individual choices. But this is just the generative model. We've then got the psi here. The psi is a common shock. It is the unobserved information that every single person observes, and it affects their happiness for all the products equivalently. You've then got epsilon. which is the idiosyncratic shock. Whenever I walk in, I get hit with different idiosyncratic shocks. And if you walk in and you have exactly the same beta as me and exactly the same psi as me, you get hit with different idiosyncratic shocks for all those products, and you might make a different purchase to me. Okay, so we're not saying that, I like a chicken hero for lunch, I buy a chicken hero every day. No, I don't do that. I get hit with different shocks every day. Now, the really important thing here for this model is that we're going to assume that epsilon is Gumbel distributed, which has a massive is a big simplifying assumption that makes it solvable very easily and computationally efficiently. Okay, the big contribution from Lewis and Suppers, and McFadden was that if this epsilon is Gumbel distributed, then we can simply take the softmax of this across all products, so the non-stochastic component of utility. If we take the softmax of the non-stochastic component of utility, that gives the the choice probability for each product. That's pretty cool. The 1 in the denominator here is because, remember, you always have that outside good. But remember, the outside good has no characteristics. It has no price. We're going to assume that the psi for the outside good is 0. Now, if you take x plus 0, it's 1, and so we just put 1 in the denominator there. But this means that what we have done is we have gone from a set of parameters. We've got our beta i's, we've got our psi's, we've got our known data, x, and now we can simulate out the choice probabilities across any large dimensional set of choices for each individual. What we haven't done yet is turn that into market shares. So I need to be able to have some way of aggregating across all of these individuals to get market shares. So the aggregate model is that our market sales are multinomial distributed around the shares vector. So this vector of shares is a simplex. It adds up to 1, all between 0 and 1. And we've got our market size. And so in small markets, you expect the observed sales to actually be a fairly noisy measure of people's true preferences, because those epsilons are giving you some variation around this true market shares. In big markets, we expect it to really zero in on that. And for shares, we simply take the weighted average across people. So if we knew everyone's betas, we've got some distribution of betas, and we just take the weighted average of the individual choice probabilities. That's really simple. The trick is how we can actually do... Oh, sorry, we're not quite there yet. First is price setting. So there are 2 ways that we do price setting. The first way, which Betancourt and Andy suggested, was we've got psi pointing at you and psi pointing at price. So psi makes me happy, psi makes the Bodega owner stick his prices up because he knows I'm going to be happy, right? And so I can't just implement psi as a random effect. It's correlated with x, it's correlated with price, okay? Also, there are as many sides as there are observations. I've only got 1 set of sales per market, and per product, and that's how many sides I have. So I'm going to have to just basically get back my prior. So we're done with that. Betancourt and Andy were like, this is an SEM, just point it at both the price and your utility, and you're fine. And that's true. So what we can do is just say price is a positively truncated normal variable, where we've got some our x's in there, we've got some instruments which are cost shifters, and we've got our psi in here with some loading factor lambda. This is clearly ridiculous. It assumes that you change your price and your competitor's not going to respond. Okay? Your competitors will respond if you change your price. Your competitors will respond if you introduce a new product or whatever. If I say I'm going to discount Beck's and I don't think that Heineken is going to change in price, or my competitor's Heineken price is going to change in price, then you're going to overpredict your sales. So we need a simple structural model here. The simple structural model is that we assume that firms are profit maximizing, so they've got price less cost times predicted sales, which is the outcome of the model. We take the derivative of this and rearrange it in terms of price, and then we just model our marginal costs here. So this is marginal costs. This is the optimal markup. And we're done.
Really?
No. Of course not. Okay. The implementation in Stan is actually pretty simple. The Berry, Levinson, and Parquez approach to this is just, let's draw some big matrix eta, which has a whole bunch of fake people. And so each row of eta is a fake person. Each column of eta corresponds to one of the columns in X. And we're just going to draw normal 0, 1. And that allows us to say that beta for each individual is simply some group mean with some L as the Cholesky factor of the covariance matrix. We're making an assumption here that they're multivariate normal, the betas are. And then we can simulate all those people's betas by just using matrix algebra. That gives us some fake betas, or some fake people. We already have psi as a parameter, and we can then aggregate over market shares. And so that's a function that just looks like that. It's a very simple function to implement. Now, so you can, or what we have done in the notebook is we simulate data from this, we go and capture data, make sure that we can capture the parameters, we're able to return the parameters. This is the one that should be biased, this red one here, the effective price, and it's not biased. Any questions, comments, or death threats?
Oh.
Can you talk about your model in relation to BLP? I assume you don't need instruments because you're, or at least you framed it as kind of a latent instrumental variable approach.
Yeah, it is latent instrumental variables approach. BLP makes the assumption that you can recover psi without the correct structural supply side model, which is quite nice. BLP also doesn't allow for any uncertainty. And so you typically have to bootstrap it or make all these limiting assumptions. It's kind of crazy. Also, BLP, it's impossible to do any cross-validation because the only way you can make predictions is with psi. They're making no distributional assumption on psi, and therefore, like... Anyone else?
Yeah, how does this space equal work? It seems like
Yeah, it's surprisingly identified.
Could you summarize the question?
Sorry, the question was, the fake people approach would seem as though it's not particularly identified. And that's kind of surprising that it is. It is identified. Thank you.